basic electronics, and the course is going to be delivered by myself, my humble self, Kabir Ahmad Abu Bilal, PhD, from Departments of Telecommunications Engineering of Ahmad Bello University, Zaria. I put my passport here, or a picture, for you to, maybe if we don't have time to do it physically, so that you can recognize the lecture. And this course, as the name implies, that is basic electronics. The postgraduate students of or postgraduate diploma students of chemical engineering are supposed to have some hints, some knowledge of basic electronics, and that is why this course is important. And let us start looking at the course without wasting much of our time. The term electronics is obtained from electron, and all of us know that the electron is one of the three particles in any atom. We have electron, which is negatively charged. We have a proton, which is positively charged, and the third one is the neutron. And the neutron is neutral, and I think that's why they call it neutron, because it doesn't have electric charge. It is not positive and it is not a negative. Now, the aspects of electronics is defined as the science or as technology that involves the motion or the movements of electrons or motion of ions, because you can have positive ions as against the electron, which is negative. So the motion of electron or a positive ion, and in electronics engineering we call it hole. We are going to discuss about that later. So the movement of these charged particles in vacuum or in gas or in solid semiconductor devices. What do we mean by vacuum? The first components that were invented for electronics system, we call them vacuum devices or vacuum tubes. We have like triodes, we have tetriodes, and many of them. But that one has been phased out. Now we are developing systems of electronics using what we call solid state semiconductors, which are the core elements in the periodic table. We are going to talk about that later. So all this electronics engineering or electronics technology is implemented based on the fundamental laws of electricity and also the laws of magnetism, as we are going to see when we go into the course. Now, as I have said, the electron is one of the three particles of an atom, and of course it is negatively charged, and of course we have what? A proton, which is positively charged. So we have two types of charges, electric charges. We have negative and we have positive. And an atom, as we all know, it has three particles, as I have already said. We have proton, we have neutron, and we have electron. The proton is positive, electron is negative, while the neutron is neutral. Now, what are the three categories we have of any matter or any material in terms of conductivity of electricity? We have three of them. We have what we call conductors, we have insulators, and we have semiconductors. These conductors are those materials that allow the movements of electric charges through them. And of course, they are basically all the metals we know. But even among the metals, some are better in conductivity than others. For instance, copper, like aluminium, all of them are good conductors as compared to other metals. Now, the insulators are those materials that don't allow the movement of electricity through them. And they include plastic, they include waxes and other chemicals which are not allowing the current or electricity to flow through them. And the third one is what we call a semiconductor. By semi, it means it is halfway. Sometimes it can be insulator, and under some conditions, it can be what? A conductor. We are going to talk about this in more details as we go in. Now, let us look at what we call the band theory of semiconductors. The semiconductors, as you can see from here, we said they are group 4 elements like carbon, like silicon, like germanium, like tin, and all the members of group 4. And they have a property in which they form what we call a covalent bonding. And you know covalent bonding is formed not by transfer of electrons, but by sharing electrons between the neighboring atoms that form that bond. And in this case, we have three regions in any semiconductor material. We have what we call the conduction band, we have the forbidden band, and we have the valence band. What do these three means? The valence band, we mean all the electrons are intact, they are fixed, they are attached to their bonding, so that we don't have any free moving charge carrier. So all those that are in that state, we say they are in the valence band. But whenever an electron has broken from its bonds so that it can be mobile, it can move from one place to another, we now say it is in the conduction band. And before you can break those bonds so that the electron can be freely moving, we need to apply some energy. And that amount of energy that we need to apply to the bonding so that we can break it and make the electrons to be mobile, the amount of energy, we call it forbidden energy. And that is what we call the forbidden band. The amount of energy, that is ionization energy, in fact, that can be used for breaking the bond so that the electron can be removed to make it a mobile free. Now, let us look at these three materials we have mentioned. We said we have conductors, which allows the movement of electricity through them. We have insulators, which do not, and then we have semiconductors, which are halfway. So if you look at these three diagrams, the first one is for the conductor, and you can see in this case, the valence band and the conduction band, they have overlap one another, meaning all the electrons, they are already freely moving, therefore they are no longer attached to the valence band, but they are in the conduction band. Just look at a metal. In metal, we learned that the type of bonding which is formed, we call it metallic bonding, in such a way that the valence electrons for each atom, they are not fixed to the neutron, but they keep on moving from one atom to another. So in this case, it means our valence electrons are already freely moving, therefore they are in the conduction band. That is why there is no any gap between the conduction band and the valence band, because we don't need any energy for us to break the electron from the bundle. But if you come to the insulator, the upper part is our conduction band, where we need free mobile charge carriers like electrons, and the lower one is our valence band, where all these electrons, they are fixed, attached to their bundle. So in between them, we have a free space, which we call the forbidden band, and this is where we need to apply some amount of energy so that we can break the the valence electrons from their bonding into the conduction mode. And as you can see here, the amount of energy needed is somehow big, around 5 electron volts. You know, 1 electron volt is 1.6 times 10⁻⁹ joule, which is very, very small amount of energy. But saying something is small or big is a relative. Okay, so therefore in this case, anything that goes beyond 5 electron volt is big as far as this is concerned. The last one is our semiconductor, and you can see also here we have our conduction band at the top, we have the valence band below, and in between them we have the forbidden band. And you can see the width, the space, the size of the space is much smaller than that of the insulator. So for this reason, we need a smaller amount of energy for us to break the electrons from the bonds and push them into the conduction band. Now, as I've already mentioned, the semiconductor materials, they are those elements which are in group 4 of a periodic table. And here we have a graph. The graph is telling us the amount of energy needed by each one for us to break the electrons from the bond so that it can enter into the conduction band. As you can see from the horizontal axis, I have my carbon C, and if you look at it, the difference between the upper curve and the lower one is very wide, which means this carbon, it has very large forbidden energy, and therefore we consider it to be as an insulator. But as you go beyond that, you have silicon and germanium next to it. You can see that the width between the two cups, that's the upper and the lower one, the width is smaller than that of the carbon. That is why we use silicon and germanium as semiconductor materials. As you go further, we have our tin here, and this tin, you can see that the difference between the upper and lower cup is very, very tiny, which means we don't need to apply any much energy. For this reason, we don't use it. We consider it to be a conductor because it requires very little, insignificant amount of energy. Now, let us look at the conductivity in a semiconductor. As I've mentioned, we call it semiconductor because in its normal form, it doesn't conduct electricity, but when an energy is applied in such a way that the bonds can be broken so that electrons from the valence band can jump into the conduction band. So let us see how that conductivity takes place. Whenever you have you are at absolute zero temperature, which is around minus 2.73 Kelvin. That is what we call the absolute zero temperature. And in that case, you find that all the bonds, all your covalent bonds are intact. And in this case, we don't have free mobile electrons, and therefore the semiconductors are now behaving as insulators. But whenever a source of energy is applied to that semiconductor, it can be heat energy, it can be electricity energy. When you apply it, that energy will be enough to break the bonds. And if the bonds start breaking, we now have fear of charge carriers. Wherever electrons goes out, it has a negative charge, and the place where it have broken from, it is what? The positive. We call that one a hole. So for this, you can find that the electrons are now in the free conduction region. So for this, we can say semiconductor now is behaving as a conductor because we have free charge carriers. Now, let us look at the actual bonding, that's the covalent bonding for the semiconductors. As we have said, they are group 4 elements, isn't it? So all these ones, you can see +4 +4 everywhere. It means this is my nucleus of the first atom, maybe of the silicon or of the germanium, because as we have seen from that graph, we use silicon and germaniums because they have medium amount of energy. And each of these silicon atoms is surrounded by 4 neighbors in such a way that it will share 1 electron with each. Therefore, it has 4 valence electrons and it will share with the 4. And each of these 4 will also contribute 1 so that you can see that the joining between each atom, we have 2 electrons, 1 at the top, 1 at the bottom, which means one supplied by this and the other one supplied by the lower one. So in this case, we can see that all the bonds are intact so that we don't have free electrons. And when that happens, the semiconductor is behaving as what? An insulator. But whenever you apply energy or heat energy or electricity energy, the molecules will now get stronger energy. They will start vibrating and they will break. The moment they break, the conductivity will start. Now, the semiconductors are categorized into 2 also. We have what we call intrinsic semiconductors and we have what we call extrinsic semiconductors. And what are the intrinsic semiconductors? They are the pure semiconductors. That is the real group 4 elements which are not doped, or we didn't introduce any foreign material to them. They are purely group 4 semiconductors. If it is silicon, everything silicon. If it is germanium, everything germanium. So in this case, you find that the number of bonds that breaks normally when the temperature rises is around 10 raised to power 11 per centimeter cube. What are we saying here? We are saying we have around 100 billion bonds broken whenever temperature rises per centimeter cube. But if you can remember the Avogadro's constant, the number of molecules we have is 10 raised to power 23, approximately is 6.202 as you know, but let's take the 10 raised to power 23 per cm cube. So if you now say this 10 raised to power 11 divided by 10 raised to power 23, you end up getting 1 over 10 raised to power 12. That is 1 out of each trillion bonds. you have 1 trillion bonds, only one is broken. You can see that 1 out of trillion is very, very insignificant. And for this reason, the amount of current that can be created is very, very small. So the conductivity of pure semiconductors, that is the intrinsic semiconductors, is very, very small, because comparing the number of bonds that are broken, 1 out of 1 trillion, 10 raised to the power 12. So in this case, you can see that if you are using pure semiconductor, the conductivity, the amount of current will be very small. And in this case, if we are dealing with the intrinsic, you find that wherever a bond is broken, a pair of charge carriers is created. The electron that has broken away, it is negative, and the place from which it breaks is positive. We call it hole. So N here in this first equation stands for the number of electrons, and P stands for the number of holes, which is positive. And if you multiply the two, will give you Ni square, where Ni is what we call the intrinsic concentration. And with respect to the temperature, this is the formula that we give you the value of this intrinsic square, that is Ni square, is equal to AT cubed, where A is a constant and the T is the temperature, exponential minus Eg. This Eg is the energy band, the energy of the forbidden band, for us to break electron from the valence band into the conduction band, where K is the Boltzmann constant and the T is what? The absolute temperature. Now, this is a graphical representation of what we have just said. And you can see on the vertical axis, I have the number of molecules broken per cm cube. And on the horizontal axis, I have temperature in Kelvin. What it is saying, whenever your temperature is around 250 degree Kelvin, only around 10 raised to the power 8 molecules will break out of 1 mole, which is 10 raised to the power 23 approximately. When the temperature rises to 300, it will increase to around 10 raised to the power 10. When it rises to 350, it will reach 10 raised to the power 12. And finally, at a temperature of 450 degree Kelvin, you have only 10 raised to the power 14 been broken out of what? 10 raised to the power 23. And even in this case, you can see that we have around 1 over 10 raised to the power 10 or 10 raised to the power 9, that is billion. So even as the temperature rises, you see that the ratio of the bonds that are broken is very, very small. And for this reason, the amount of current that could be created is also very small. So that is telling us that using intrinsic semiconductor materials is very ineffective, because it does not give amount of current, large amount of current that can flow. So now we come up with another idea. We call it extrinsic semiconductor, or we call it doped. This doped is obtained from the word doping, and the doping is nothing but introducing a foreign material into a pure semiconductor. And as I've already said, the amount of current that is obtained is around 10 raised to the power minus 9 amperes. That is 1 over 1 billion amperes, which is very, very small, though the 10 raised to the power minus 9 is missing here mistakenly, but it is 10 raised to the power minus 9 amperes. So this current is very small. If you want to increase the flow of current in semiconductors, definitely you have to introduce impurities. And these impurities is introduced using what we call doping. That is a process of injecting another group element into the what? Pure semiconductor materials. And the impurities that we normally introduce, they are either group 5 or group 3. When you introduce group 5 elements like phosphorus, like arsenic, all of them, they are group 5. They have 5 valence electrons. And when you introduce group 3, like boron, like aluminium, they have 3 valence electrons. Now, let us see how that actually happens. Whenever you, so as we've said, the foreign elements that we normally introduce to create an extrinsic semiconductor are either group 5, example phosphorus, arsenic, or group 3, like boron or aluminium. So whenever you introduce a group 5 element into the pure semiconductor, which is group 4, it means those 5 valence electrons of the group 5, like phosphorus, 4 of them will be shared with 4 neighboring silicon atoms, and then there is 1 extra electron which is not bonded to anything, which means we have an excess electron free. And we know the charge of electron is negative, and that is why we call this type of extrinsic semiconductor, we call it N-type, that is a negative type. And if you introduce group 3, you know, they have 3 valence electrons, and you now introduce them into a pure semiconductor of group 4. So these 3 electrons, like that of boron, will now be shared with 3 out of the 4 neighbors. Then the last neighbor, it means the boron cannot supply electron that can fill that place. And for this reason, where the electron is missing, we have what we call a hole, which is a positive charge. That is why we call this one a p-type semiconductor. Now, this is a representation of what I have just said. If you look at the left hand side here, you can see plus 5, which is the group 5 element introduced, surrounded by group 4 elements. And as I've said, 4 out of this 5 will be shared with each 4 of this neighboring, and at the end of the day we have 1 extra which is not connected, and this is our free electron, and that is why we call this one N-type semiconductor, negative type. And on the right hand side you can see we have plus 3 here, which is the group 3 element introduced like boron, and it is surrounded by group 4 elements or atoms like that of silicon. So this will share 3 with the 3 neighboring, then the 4th one doesn't have any electron to give, and for this reason we call this one a hole where the electron is missing. And the charge of a hole is what? A positive charge, and that is why we call this one a p-type semiconductor. Now if we consider, we assume this p is the number of the positive charge, which is the holes, and n is the number of negative charge, which is what? The electrons. And we assume this Nd is the concentration of the group 5 element we introduce. We call this one Nd because D stands for donor. If you introduce group 5 into group 4, it will share 4 out of its 5 valence electrons, and it has additional extra electron, so it can donate it whenever needed. That is why we call it donor. But if you introduce group 3, we told you that there is a place where we are missing an electron, and that place we call it what? A hole. So it means we need 1 electron for us to complete this place, and for this reason we call this one Na, that is acceptor, the concentration of the acceptor. So now the formula that is connecting these 4 variables, the P, the N, the Nd, and Na, is given by this, where rho is the charge density, which is called the Q, that is charge of electron, 1.6 times 10⁻⁻19, into P, the number of holes, minus N, the number of electrons, plus Nd, the number of donors, that is group 5 impurities, minus Na, the acceptors, that is group 3 impurities. Now let us consider, or let us talk about what we call the minority and the majority carriers. If we go back here where we introduce group 5 elements, as I told you, 4 out of the 5 valence electrons are shared by the 4 neighbors, and we have an extra electron. So it means we have more number of electrons than required. So even when the bonds have been broken, you find that electrons will be more than the holes, because we already have existing free electrons before the breakage of the bond. So let us, as we said, we're going to look at minority carriers, and of course it means there are majority carriers. In any semiconductor where your donor, that is group 5 impurity, is equal to your acceptor, that is group 3 impurity, it means when they are equal to 0, it means that semiconductor is pure. You didn't introduce either group 5 or group 2. In this case, you find that the number of electrons is equal to the number of holes, and this formula, Np equal to Ni square, holes, where N is the number of electrons and P the number of holes. So we can represent each one of them by Ni, that is the intrinsic. And whenever you are dealing with N-type semiconductor where you introduce group 5, you find that the holes are the minority carriers, and the formula for calculating is given by Ni square over Nd. And in a situation where you are dealing with group 3 impurity, that is where you have p-type semiconductor, you find that the electrons are the minority and they are given by Ni square all over Na, where Na, as we said, is the concentration of the acceptors. Now let us look at the movement, that's the transportation of electric current. There are two modes in which the electric current can flow in a semiconductor, either by what we call the drift or by diffusion. These are the two methods. The first one, that's the drift, or rather the second one, the diffusion, is a movement of charge carriers, electrons, and the holes whenever there is rise in temperature. Rising in temperature, it means more kinetic energy to the molecules and they will start vibrating, and that vibration will push them to be moving around in the semiconductor, and that causes movement of electrons, and the speed of those charge carriers is given by this, that is B subscript th. Th stands for time, is equal to the square root of 3 kt over m, where k is the Boltzmann's constant, m star or m asterisk is what, the effective mass of the charge carrier electron. So the only variable is what, the T, the temperature. Whenever the temperature increases, the velocity will also increase. Then we have the second one, which we call the drift, that is whenever you apply electricity. The diffusion is for the heat, the drift is when you apply electricity. And if you do that, the electric energy also will push these molecules in such a way that they can start moving. And the velocity of the charge carriers, as we have said, we have either electron, which is negative, or the hole, which is positive. So the velocity of the hole is given by mu h E. This capital E is what? The electric field intensity, and the mu h is the mobility, is a constant mobility of the hole. And in this case, mu E is the mobility of the electron. And the mobility of the electron is much better or bigger than that of the hole, because in reality, it is the movements of the electrons that brings about the movements of the holes. Now, if you want to calculate the drift current, that is the current created as a result of the flow of this a charge carrier's electron, for example, within or through a conductor. We assume this diagram, this is our conductor, and it has a length of L from here to here, and the cross-sectional area is A. Now, if we want to do that, we now say the current, as we know from our secondary school physics, current is equal to charge per unit time, and NQ is the total charge, where Q is charge of a single electron and N is the number of electrons. So multiplying the two will give us the total charge over time. And if you wish, you can manipulate this one by saying NQ, which is what we have here, times L over T. We introduce a foreign T, L here, then you put it here because they can cancel out. So this L over T is the velocity because it's the distance over time. Now my current, this formula, can now be equal to NQV, where V is the velocity all over L, which is the length. And we now have another parameter G, we call it the current density, that is the total current per unit area. So your G is now equal to this current all over area, which is the same thing as NQV all over AL. This is the L A we introduce here, the L is already there. And the value of this current density for the movement of hole is given by this formula, Q P mu H of E, where Q is the charge of electron 1.6 times 10⁻⁹, and the P is the number of holes, mu H is the mobility of the holes, and E is the electric field intensity. For electrons, we have N and mu E instead of P and mu H. So if you want to find the total current density, you add that of the hole to that of what? The electron, and this will give you this formula. And also, we have another variable, which is the conductivity, and the conductivity sigma is for the hole. The sigma H is equal to Q P mu E mu H m, and for the electron, sigma N is Qn mu E, where Q in each case is the charge of electron, N is number of electron, P is the number of holes, and the mu is for the holes and the electron respectively. So if you add these two also, the total electric conductivity is given by Q, because you can see Q is common here and here. We factorize it out, then we have P mu H plus N mu E. Now, for us to demonstrate how to use this formulas we have derived, we are given a question here which says we have a conductor, the length is 2.8 millimeter as you can see from the diagram here, and the cross-sectional area is A, and the current passing through that is 5 milliampere, and this will produce a voltage, that's the voltage drop of 100 millivolts. 100 millivolts across the material, and we are given that the mobility of the electron is 500. So now we are asked to determine the electron concentration in this line of the conductor. They said it's a conductor line in an IC. IC stands for integrated circuit. Now let us see how we go about solving this problem. First of all, these are the given values. The current is given in milliampere, so we multiply by 10 raised to power minus 3. The voltage also 10 raised to power minus 3. The length is 28 milli, then we multiply by 10 raised to power 3. The mu, that is the conductivity, 500 centimeter square per volt second. So since it is centimeter square, we want to change it to meter square. For you to change from centimeter to meter, you multiply by 10 raised to power minus 2. So since the centimeter is square, it should be 10 raised to power minus 4. And the length of the rectangular cross-section of that conductor is given by this. Each one of them is in micro, as we can see from this. This is 4 micrometer and this is 1 micrometer. So if you multiply, it will give you 10 raised to power minus 6. 10 raised to power minus 6 for each one. That will give you 4 times 10 raised to power minus 12. Now, if we want to find the concentration, which is the N, we start using this formula, which says the conductivity is equal to length all over Ra. And we know R is a resistance. From the Ohm's law, R is equal to V over L. So since my R is there on there, that is denominator, then I should go up and the V should come down. So I'm given my current, see it here, my length, see it here, and the voltage is given 100, and the area is what I have just calculated here. So if you simplify everything, you end up with 3.5 times 10 raised to power 10 raised to power, is it 5 or 6? I mean 7 per ohm meter. Now this is the conductivity, but what they said we should find is the concentration, which is the N. And from this formula, the conductivity or conductance is equal to Qn mu E. So which means N is equal to sigma, the conductivity, all over Q mu E or mu N. The sigma is what I have just calculated, all over Q, the charge of electron, and the mu H is the conductivity, the mobility of electron given. And if you simplify, you end up getting 3.5 times 10 raised to power 21 all over 8. You can divide the 3.5 by 8 to get the final answer. So ladies and gentlemen, if any lady at all, I know engineering is for gentlemen mostly. This is the end of our introductory lecture, which is the lecture number 1. I advise you to watch this thing over and over again. Definitely it will be helpful. You can understand it better. Till we meet in our second lecture. Thank you very much.